তোমরা শুনতেছো আমাকে?
জি স্যার, শোনা যায়।
ওকে, একটু নেটওয়ার্কটা সমস্যা করতেছিল, আমি এই ঢুকতে একটু কষ্ট হয়ে গেছে। এনিওয়ে, তো আমি তাহলে শুরু করে দিই, লেকচারই শুরু করে দিই, যেহেতু অলরেডি টাইম ওভার হয়ে গেছে। তোমরাও আছো কত, 53+। একটু রেকর্ডিংটাকে অন করে নিচ্ছি। Okay, so I am requesting all of you to attend in the class, to concentrate in the class, otherwise it will not be fruitful. Okay, the class will not be fruitful to you. So I am requesting all of you to attend in the class sincerely. Just not to log in and you are working your work, you are doing your work. It is not a good practice. And when I finish, when I will finish the lecture, then I will be done. Okay, and then the output, or how much you have learned from my lecture, or how that will be very much useful for you. So I am requesting all of you to attend sincerely. So today, in the last class, I told you that I will give the lecture on deflection today. Okay, I'll give the lecture on deflection today, and as I have already told you that there are many methods to calculate the deflection of a structure due to the applied load, and the most important, not most important, the important method among those methods is integration method. Okay, so I will discuss the integration method briefly today. The theory will be discussed today, and some problem will be discussed in the or explained in the next class. So is this slide visible to all of you?
Yes, sir.
Okay, and if I set it full screen, is it visible now?
Yes sir, visible.
Yes, sir. Visible.
Okay, thank you very much. Okay, so actually, if any structure, or if any beam or any shaft of the structure. So what is response? Response is the deformation or a stress developed in the beam or a structure due to the applied load. That is the response. Okay, response means basically it is nothing but the deflection and rotation. That will be the response of any load due to the response of any load to any structure. So if we show the response or the consequence of applied load, it will be similar to this one. So that means if any structure is subjected to any applied load, or if we apply any loads to any structure, then the structure will be deflected. The structure will be deflected, and due to the deflection, there will be a curve. And from the curve, we can calculate the curvature. Curvature is nothing but the change of slope, change in slope of the curve. Okay, that is curvature. And due to the curvature, the bending stress will be developed. That is the final response in the structure due to the applied load. Okay, so first of all, if we apply load, then the structure will be deflected. That means the shape will be different from the original shape. And as the structure will be deflected, or beam will be deflected, there will be curvature. As there will be curvature, it means that there will be bending moments, or sorry, bending stress. There will be a bending stress, and it is simply represented or shown by this diagram. This guy is hanging on this rod. Okay, so due to the weight of the guy, the shaft has been deflected. Okay, shaft has been deflected. So as the shaft has been deflected, so there is a curve. There is a curve. As there is a curve, so there will be curvatures at different points. So as there will be curvatures, so there will be definitely bending stress. So those are the consequences of applied load to any structure. And this slide is visible.
Yes, sir.
Okay, thank you. Because I am asking you because in the last class, sometimes the slides were not visible. Okay, so as it is a new topic, so you will see some new terms. Say one term is elastic curve. One term is elastic curve. So what is elastic curve? Elastic curve, that means, say, assume it is a beam, and this beam is homogeneous beam. That means cross section is homogeneous. That means the cross section at each point along the length of the beam is same. So the centroid of each cross section will be along the horizontal axis. Along the horizontal axis, because the section is homogeneous. So there will be many sections, right? If you cut the beam here, here, so there will be many cross section. And if you cut the section here, then you will get a cross section. Then you will have a center of that cross section. Similarly, if we cut the section beam here, then you will get another cross section. Then you will get another center of the area. Then if you cut the beam here, then you will get another cross section, and you will get another center of that area. And if you connect the center of area, then ultimately you will see that it will be a straight line, and it will be along the horizontal direction. Okay, along the horizontal direction. Now, if the beam is subjected the center of the cross section will not be along the horizontal direction. It will be shifted up or downward. So it will be shifted along vertical direction. It may move upward or it may move downward depending on the applied load. Okay, and in that case, again, if you draw the center of each cross section, then you will get a line. You'll get a line that will be similar to this one for this type of problem, and this line or this curve is known as elastic curve. Okay, so what is elastic curve? It is the deflection diagram of the longitudinal axis. It is a longitudinal axis, right? The deflection diagram of the longitudinal axis that passes through the centroid of each cross-sectional area of a beam or shaft. Okay, that is known as elastic curve. So is it clear?
ডিফ্লেকশন ডায়াগ্রামটা দেখা যাচ্ছে না স্যার।
স্যার আমরা তো স্যার মনে হয় দেখতেছি ওই যে একটা লোক ওই যে এখনো হ্যাঙ্গিং করে আছে এক জায়গায়, ওই জিনিসটা দেখতেছি, অন্য স্লাইডগুলো দেখতেছি না।
Okay.
Slide number 1 এ
now is it visible?
স্যার এটা এখন আসছে, মাত্র আসছে, আগে দেখা যায় না। স্যার এখন আসছে স্যার।
Okay, ঠিক আছে। Okay, so look at the first figure. So if we cut the beam at here, if we cut the beam here, then you will get many cross-sectional area, right? You will get many cross-sectional area, and if the beam is homogeneous, that means the cross-section of the beam is uniform. Cross-section of the beam is uniform. So if you cut here the centroid of the area, if you cut here centroid of the area, if you cut here centroid of the area, and if you connect all centroidal point of the area, then you will see it will be a straight line. It will be a straight line along the longitudinal direction. Okay, it will be a straight line along the longitudinal direction if the beam is not subjected to any applied load. But if the beam is subject to this type of load, then the centroid of the area here it will move down due to this load. Similarly, the centroid of the area at here, it will move down. And the movement of the centroidal point will not be same at each point, right? So it will be different at different point. Now, if we connect the centroidal points of different cross-sectional area, then you will get a curve something like this. You will get a curve something like this. And this curve is known as elastic curve. Okay, this curve is known as elastic curve. So that is elastic curve. So what is elastic curve? It is the deflection diagram of the longitudinal axis. Yeah, this is the longitudinal axis, and it indicates this one. This curve indicates the deflected shape. Originally, the longitudinal axis was horizontal for this problem. It was horizontal. Okay, and due to this applied load, the horizontal axis or the longitudinal axis has been shifted here. So that is the deflected shape of the longitudinal axis. Okay, longitudinal axis, and that axis passes through the centroid of each cross-sectional area. In that case, that is known as elastic curve. And look at the second figure. Again, look at the first figure. So there are two supports. This one is hinge support and this one is fixed support. Okay, hinge support and fixed support. So what is fixed support? Fixed support means that support can resist rotation. That support can resist any kind of translation. Translation, that means movement along vertical direction or movement along horizontal direction. Okay, movement along vertical direction, movement along horizontal direction, that is translation. And rotation, that means this beam may be rotated, or as it will deflect, so it will rotate at by different angles at different points. Okay, so this one is hinge support. So this support has no capacity to resist rotation. Okay, so to resist rotation, so there will be deflection. There will be rotation. But as it is a roller hinge support, so it cannot move upward. So the original centroidal axis was there. At this point, it is still here. Okay, because as it is a support, hinge support, so it will not move upward. And again, as it is a roller support, a hinge support, so it will not move along horizontal direction. So this point initially was there, and still it is there after applying load. But this support is fixed support, so it will not move along horizontal direction, it will not move along vertical direction, and it will not rotate. It will not rotate. So the shape, the deflected shape of this curve, the deflected or the diagram of this curve will be such that at this point the rotation will be 0. So rotation means what? Rotation means, say at this point, the rotation means if you draw a tangent at this point, if you draw a tangent at any point on the curve, then the slope of the tangent, indicates the rotation of that point. Okay, slope of that point is will indicate the rotation of that point. So here the rotation will be 0. Rotation will be 0. That means if you draw the tangent at this point, it will draw the tangent at this point. The slope will be 0. That means the point, the line was horizontal initially. It will be still horizontal. It will be still horizontal at this point because there will be no rotation as it is a fixed support. So, okay, so the shape of the curvature at this point is something like this. That means slope will be 0 at this point. Okay, and now we'll come to the second figure. And second figure, again, there are two supports. One is roller, another one is hinge support, and it is subjected to the applied concentrated force P at the end of the cantilever part. This part is known as cantilever part. Excuse me. And imagine what will be the deflected shape. It will be similar to this one, right? It will be similar to this one. That is the deflected shape of this centroidal of the horizontal axis. Okay, due to this applied force, this point will move upward or downward, and as this part will move downward, so this part will move upward. This part will move upward, and there will be no vertical direction movement. There will be no vertical movement as it is a roller support, but it can move laterally. It can move laterally. So initially this point was here. Now it is here. Now it is here. Okay, and it is hinge support, so there will be no horizontal translation, vertical translation. So it is still here. But as it is a hinge support, so it cannot resist bending moment or rotation. So there will be rotation. And this is known as the elastic curve of this beam. Okay. And now sign convention. Already you are familiar of this sign convention. So I am still just recapping. Okay, I am just recapping it. So we know there are two types of moments: positive moments and negative moments. Generally, the positive this type of moment is positive moment. That means here the curvature of the curve of the deflected shape will be downward. Okay, concave upward, or the curvature will be downward. Okay, and this is known as negative bending moment. That means if the beam deflects upward, if the beam deflects upward, that is negative bending moment, and if the beam deflects downward, it is positive bending moment. And now, how we can draw the elastic curve of any beam? How can we draw the elastic curve for any beam? So it is explained by two examples here. So this one is first example. It is a beam. It has again two supports. One roller support at this point B and another hinge support at point D. And this beam is subjected to two concentrated force. One is at the end of cantilever part, and another is between B to D. Okay, between B to D. So to draw the elastic curve, first of all, we have to draw the bending moment diagram of the beam. We have to draw the BMD, bending moment diagram of the beam. And to draw the bending moment diagram, if you are very much expert, or if you have enough knowledge about the shear force and bending moment diagram, then you can draw the shear force bending moment diagram without drawing shear force diagram. But if you are not so expert, or if you are not so familiar with the shear force and bending moment diagram, then you will follow the general procedure. What are the general procedures? To draw the bending moment diagram, first of all, you have to calculate the reactions. Okay. Then you will draw the shear force diagram. When you will have the shear force diagram, then you will draw the bending moment diagram. Okay. So that is the bending moment diagram. But learn how to share. I am not doing that part here because I need only the bending moment diagram to draw the elastic curve. That's why I am showing you the bending moment diagram for this beam due to this this kind of applied force. Okay, basically you have to calculate the reactions at here, then you will draw the shear force diagram, then you will draw the bending moment diagram. And typical bending moment diagram for this type of beams and this type of loads will be similar to this one. Okay, will be similar to this one. That is the typical bending moment diagram, although the magnitude or the size of the bending moment diagram may vary depending on the applied force and location of the applied force. Okay, location of the applied force. Say, at this point the moment is 0, but it depends on the value of this applied force. Due to the applied force, this point may shift leftward, or this point may shift rightward. Okay, but the shape will be similar to this one. Okay, shape will be similar to this one. That means there will be a triangle, and there will be another triangle. There will be another triangle here. Okay, and you will get a point along the x-axis where there is no bending moment. At where there is no bending moment. So the shape of the typical shape of the bending moment diagram for this type of beam due to this type of bending applied load will be similar to this one. Okay, so this is negative bending moment and this is positive bending moment. This is negative, this is positive bending moment. So from the previous side convention, we have seen that due to negative bending moment, the beam will deflect upward. And due to positive bending moment, the beam will deflect downward. Okay, so come here. So this is negative bending moment, right? So it will deflect upward. As it is negative bending moment, so it will deflect upward. And it is a positive bending moment, that means it will deflect downward. Okay, so this part will, so from this point to this point, that means from A to C, this part will deflect upward. This part will deflect upward. And from C to D, there is positive bending moment, so this part will deflect downward. Okay, this part will deflect upward and this part will deflect downward. Okay, so to draw the diagram, the complete diagram, simply if you draw the diagram parts by parts, say if you draw the deflected shape of this part, then you can simply show the deflected shape something like this, upward curvature. Okay. And if you draw the part separately, then you can show it will be a downward curve. It will be a downward curve. But if you draw the complete curve, deflected shape, then what will be the final? What will be it? Okay, to draw the deflected shape, you have to keep your mind about the support condition. So it is roller support. That means this point will not move along vertical direction. Okay, this point will not move along vertical direction. So at this point, deflection is 0. And again here, but as it is roller support, it has no capacity to resist rotation. Again here, come to another support B. So it is hinge support. So again, it will not move along vertical direction. And it will not move along horizontal direction. So vertical movement, horizontal movement is restricted here. But as it is hinge, so it has no capacity to resist rotation. So there will be rotation. Okay, so there will be rotation. So if you draw the shape, it will be deflection will be 0. So it will be similar to this one. Deflection here 0, and it will come here. So because within this part, the deflection will be upward. And here the deflection will be 0. So the curvature, the curve will go something like this. So come to here. Look at the third figure. So the deflected shape is something like this. Okay, so this is the deflected shape of this part from A to C, and the deflected shape of from C to D, it will be here because it will be a continuous line. It will be a continuous line because initially it was here. Now it will be it has been shifted here, so it will be a continuous line. Okay, there will be no gap between these two parts. There will be no gap. It will be connected. Interconnected. So this part, this downward curve will start from here. So this downward curve will start from here. It will go and it will be here. So this is the deflected shape of the centroidal longitudinal axis. Centroidal longitudinal axis, and this is known as elastic curve. Okay, elastic curve, and this is the general procedure to draw the elastic curve. So first of all, you will draw the shear force, you will calculate the reactions, then you will draw the shear force diagram, then you will draw the bending moment diagram. But if you are very much expert about the bending moment diagram, or if you have enough knowledge about the bending moment diagram, then you do not need to draw the shear force diagram. Okay, you can draw the bending moment diagram directly. Okay, then when you will have the bending moment diagram, then you will draw the deflected shape. Okay, it is the deflected shape. Although this diagram will not show the will not drawn according to the scale. Okay, this diagram will not drawn according to the scale. Just it will give about the idea what will be the curvature of the deflected shape. It will give you some idea about what direction. Will it be upward or will it be downward? It will give you that idea, but it will not give you what will be the exact value. What will be the exact value that you cannot calculate it from the elastic curve. Okay, and one important thing that is look at point C. Look at point C. So if you want to calculate the rotation at this point of this curve, okay, rotation of the beam at point C towards right. So to calculate the rotation, you have to draw a tangent at this point to this curve. You have to draw a tangent at point C to curve ABC. That will be something like this. Okay, and that slope indicates the rotation of point C. Okay, rotation of the beam at point C. Is it clear? Anybody respond, please?
Yes, sir.
Are you hearing me?
Sir.
Okay. So, and come to this right point. So at here again, if you want to draw the rotation of the beam at point C toward right, what will be the rotation? To calculate the rotation again, you have to draw a tangent at point C to this curve. At point C to this curve. Okay, so and that that will be downward, and this angle will indicate the rotation of the beam CD at point C. Okay, so look at point C. So at this point there are two rotations. One is upward and another one is downward. There are two rotations. One is upward, another one is downward. And this point is known as inflection point. Okay, this point is known as inflection point. That means that point will have two rotations. One is opposite to each other. If one is clockwise, another one will be anti-clockwise. Okay, one will be clockwise, another point will be anti-clockwise. That is known as inflection point.
Sir, rotation activity बोलते हैं.
Rotation, that means if you want to calculate the rotation of this part, because this part will move upward, so there will be a rotation of this part at point C, and rotation will be different at different points. But if you want to calculate the rotation at point C towards left, you have to draw the tangent to this curve at point C. That will be here, something like this. The tangent will be something like this. Okay, and the slope of this tangent with respect to the horizontal axis indicates the rotation of this point. Okay, indicates the rotation of this of the beam at this point. So in this case, so rotation will be this one. Okay, again at point C, if you consider this part, and if you want to calculate the rotation, so you have to draw the tangent. You have to draw the tangent at point C to this curve. So it will go down. It will go down, and this angle will indicate the rotation of this part at this point. Okay, so this point has two rotations. One is this upward, another one is downward. One is upward, another one is downward. So this type of point is known as inflection point. Inflection point, that means if you draw a line at this point, and that line will be tangent to this curve, and that line will also be tangent to this curve. That line will be tangent to this to both curves, and that is known as inflection point. Okay, or simply we can say at the inflection point bending moment is 0. And inflection point bending moment is 0.
স্যার এই জিনিসটা আরেকবার বললে ভালো হতো
Okay.
স্যার, কথা বা ফোন
And
করতে
the cantilever beam it is fixed of rotation, it can resist translation. কোনখান থেকে বলো তো? Okay, no problem. I am explaining this one, it will be very much clear to you. So this is a cantilever beam again, and support is at A, it is fixed support. It is subjected to two kinds of loads. One is concentrated force P, another one is concentrated moment M at the end. Okay, so as it is fixed support, so it cannot translate along horizontal direction and along vertical direction. And again, it will not rotate. It will not rotate. That means there will be no translation along horizontal direction, no translation along vertical direction, no rotation at this point. No rotation of this point. That means the okay. I will explain it here. Okay, so to draw the elastic curve, first of all, again we need the bending moment diagram to identify the curvature of the beam. Okay, to identify the curvature of the deflected shape. To get the idea about the curvature of the deflected shape, we need the bending moment diagram. So similarly, similar to previous one, you will calculate the reactions here, and then you will draw the shear force diagram. Then ultimately you will get the bending moment diagram, and it will be similar to this one. And again, the size of the bending moment diagram may vary depending on the applied load and depending on the location of the applied load. But the shape will be similar to this one. So here, this one is negative bending moment, this one is positive bending moment. So a negative bending moment, that means this part will move upward, or this part will be curved upward. And it is positive bending moment, so this part will be deflected downward. Okay, this part will be deflected downward. So this part will be deflected upward, this part will be deflected downward. Okay, so that means this part will be upward and this part will be downward. And one thing here, it is fixed support. It is fixed support, so you can draw a curve at this point either this way or either this way, right? As it is fixed support, so a tangent will be 0 here. A tangent will be along horizontal axis. Excuse me. Is it clear? As it is fixed support, so the tangent to the deflected shape will go along x-axis, because it is fixed support, so there will be no rotation. There will be no rotation. So we can draw two lines. One is something like this. At here, curvature or rotation is 0, then it can go like this way, and we can draw another one. At here, it will go this way. Okay, it will go this way. So which one will be corrected one for this problem? This one or that one? Which one will be accepted curve? This one will be accepted. This one will be, because it is negative bending moment, so it will move upward. Curvature will be upward. So this curve will be accepted. So look at here. It is this one. Okay, at this point the curvature is 0. That means there will be no slope. So initially it will go straight, then it will go down. It will go down. Okay, at this part it will move downward. So here this one is moving downward. So that is the deflected shape of the longitudinal centroidal axis. Okay, so this is the general procedure to draw the elastic curve for any kind of structure. And now, what is the relationship between curvature. Here it is hinge support, and at this end it is roller support. And this beam is subjected to three types of load. One is distributed load, W. This one is distributed load. It may be uniform or it may not be uniform. And this one is okay. Curvature means curvature is the inverse of radius of curve. That is known as curvature. Okay. If radial relationships between moment and curvature. So if we want to draw the relationships, so we can consider a small element along the length of the beam, and the length of the beam is dx. Length of the element is dx. So this is the exaggerated shape. That means this it is nothing. There will be no equals to my divided by I. M times y divided by I. M is the bending moment. Y is the distance of any point from the neutral axis, vertical distance, and I is the moment of inertia. So it indicates that the stress is varying linearly. It depends on y. If the magnitude applied moment is constant, then it will vary depending on the distance from the neutral axis, y. Okay, so neutral axis means it is an axis where there is no flexural stress. There is no flexural stress. That means due to bending moment, there will be no stress. Due to bending moment, there will be no stress. That is known as neutral axis. So this one is neutral axis. That means along this line, there is no stress. Okay, along this line, there is no stress. Okay, and we can consider another segment here that is located y distance from the neutral axis, and the length of the segment is ds. Length of the segment is ds. So this figure shows the section before applying load. Okay, before applying load. So this figure shows the section before applying load. And if we apply load, definitely it will move, it will be deflected. The beam will be deflected, something like this, right? It will be deflected downward. So it will be deflected downward. That means top part will be compressed and bottom part will be extended. Okay, top part will be compressed and bottom part will be stressed. That means it will be elongated. Okay, so the deformed shape is showing by this diagram. This is the deformed shape. So the top part will be compressed. That means it will be shortened, and bottom part will be extended, stressed. And as it is a neutral axis, so there will be no stress. So as there will be no stress, there will be no deformation. Because according to Hooke's law, we know as it is neutral axis, there is no stress. This length will be similar to previous one, dx. Okay, but as it is not a neutral axis, so this length will not be similar to this one. It will be different from this one after deformation. So it is this ds prime. Okay, and now if we extend this line and that line, oh, okay, another thing, according to beam theory, according to assumption, we know that the plane section remain plane before deformation, after deformation. So this is a plane section before deformation, so it will remain plane after deformation. So this section is remain plane before deformation, so it is plane section before deformation, so it will be plane still after deformation. Although it can rotate, but it will be plane. So if we extend this one, this line, this space, and if we extend this space, ultimately they will meet at this point, O prime. Okay, so this point is known as the center of curve. Center of curve. Okay, and the distance from the center of curve to any point on this on the depth is indicated by rho. Okay, so rho indicates the distance from the center to any point along the thickness of the section, and the angle between these two faces is d theta. Okay, and according to linear elastic manner, that means elastic curve, it means that the material is linear elastic. Material is linear elastic. That's why it is elastic curve. Okay, for a linear elastic manner, we can show these relationships between curvature and strain. This one is curvature 1 by rho equals to minus epsilon by y. Epsilon is the strain. Epsilon is the strain. And we know epsilon or strain equals to sigma. That means stress by modulus of elasticity E. That means epsilon will be equals to sigma by E. And if we substitute here, it will be here, this one. Stress sigma by E divided by y. Y is the distance from the neutral axis. Okay, and again we know stress equals to my by I. Already I have told you. My by I. So if you substitute it, then the final relationships is this one. So this part, this side indicates the curvature, and it is the moment. It is the moment. That means this is the relationships between curvature and moment. Okay, and slope and displacement by integration. As I have already told you that we can calculate the slope and displacement by different methods, and one well-known popular method is integration method. Okay, integration method. So again, if we consider this diagram, so this horizontal axis indicates the longitudinal axis of the beam, and due to the applied load, the deformed shape, the beam will not be horizontal; it will be deflected downward for this type of movement applied load. So the deflection or the movement is indicated by V, indicated by B. So that is the deflection along Y direction. Okay, and as the applied loads are not constant, it varies from point to point. So the deflection will not be constant along the length. It will vary from point to point. Any question? Okay, so we can say the deflection is a function of x. Deflection is a function of x, and applying the mathematical operation to this deflection shape. Finally, we can see that 1 by rho equals to d square v by dx square, d square v by dx square, sub row number 22. This mu. Okay, so the final expression of curvature will be this one in terms of differential equation, and that is nothing but m by ei. Here, the deflection, as the material is linear, elastic part, so the deflection will be very much small. So the dv by dx, dv is the deflection and dx is the length. So this term will be small. So if we square it, it will be small. That means it will be less than 1. So if we square it, it will be very much small. So we can neglect this part with respect to other part. Okay, we can neglect this part with respect to other parts. So it will finally it will be EI d square V by dx square equals to M. Okay, so now if we differentiate this both sides with respect to x, then it will be d this part divided by dx. D by dx, this part equals to dm by dx. dm by dx. And we know from the relationship between shear force and bending moment diagram, if we differentiate moment diagram with respect to x, then we can get the shear force at that point. Okay, we can get the shear force at that point. So we can replace dm by dx by v. V is the shear force, and again the shear force may vary from point to point, so it will be a function of x. Again, if we differentiate this term with respect to x again, then it will be this one. Okay, and it will be dv by dx. dv by dx, again we from the relationships between the applied load and shear force, we know that differentiation of shear force diagram will indicate the distributed load. Will indicate the distributed load. So it is this one. Okay, this one. So this is the so finally this equation will be minus W is the distributed load, and it may vary, so it will be a function of x again. Okay, and so the sign conversion. So okay, so actually we will calculate the deflection. So we will use this equation, or this equation. So to calculate the deflection, we have to integrate this equation for 2 times. With respect to x, we have to integrate this equation for 2 times with respect to x. Then we can get the value of v. V is the deflection. Similarly, if we have the shear force relationship, then we can integrate this one, and then we can integrate this one to calculate the deflection. So I will explain it in the next class with respect to different examples. So again, the sign convention, I have already shown it. This moment is positive moment, and this type of shear force is positive shear force. Left side, right side downward positive, left side upward positive. And this is the positive deflection. Upward deflection is positive. Upward deflection is positive. And say if the x6 along rightward direction, x6 along rightward direction, and to calculate the rotation at any point, say if we want to calculate the rotation at this point, then we will draw a tangent. It is the elastic curve. This is the elastic curve, so we will draw a tangent at this point. So this is the tangent. This is the tangent at this point, and then we will start from the horizontal axis and we will go along the anti-clockwise direction to the tangent to calculate to measure the rotation. So we have to draw it at any point to calculate the rotation. So this is the tangent, and we will start from the horizontal axis along the anti-clockwise direction up to that tangent to measure the rotation, and this is positive rotation. If condition is if x is along rightward direction, okay, x is along rightward direction, and but if x is along leftward direction, then we will start from x-axis, but we will move along clockwise direction. Along clockwise direction, that will be positive moment. And coordinates. So this length is ds, or exact length is dx, and this one is vertical direction. Coordinate is dv, and the length is segment length is dx. So the final length is this one, and so it will form a triangle, because as it is a very small, so we can, it is a straight line, not a curve. It is a straight line, so it will be a right angle triangle. So apply the Pythagoras rule, that d square x will be this one. Okay, d square x will be this one, and finally we can write it this way, dv by dx, and again we have already shown you that dv by dx is very small. So if we square it, it will be very small. That means this part we can neglect. So dx will be ultimately approximately equals to dx. Dx approximately equals to dx. So what is the conclusion of this equation. It concludes that this point, say initially this point was here, now it is here, as this length and that length are almost same, so we can say this point will move only vertical, along vertical direction, no x or no y, no horizontal. Okay, that means there will be no horizontal translation, it will move only vertical direction. Okay, and again, if the slope is very small, then we can say that theta equals to approximately tan theta, and tan theta is dv by dx. Okay, and this is the boundary condition and continuity condition. If the support condition is roller, so the deflection along the vertical direction is 0, and moment carrying capacity at this point is 0, and say a point is 0. So the class, if you have any question, please you can ask me. একটু আমি পরে, আমি একটু ক্লাসে আছি তো, আপনি 10 মিনিট পরে কথা বলেন। ওকে, do you have any question, please? You can ask.
Yes, sir.
Any kind of question.
স্যার এখানে যে স্যার ডিভি বলছিলেন, স্যার ডিভি কি স্যার শেয়ার ফোর্স?
হ্যাঁ, কথা বলো তো
স্যার ডিভি
এখানে ফিগার দেখতেছো?
স্যার স্লাইড
হ্যাঁ,
থেকে
DV এটা
স্যার স্লাইড তো স্যার দেখা যায় না।
ও স্লাইড দেখতেছো না, সরি। দেখো ডিবি মানে এই ডিবি।
জি স্যার এই ডিভিটা স্যার,
এই ভিটা হচ্ছে শেয়ার ফোর্স, আর স্মল ভিটা হচ্ছে ডিফ্লেকশন।
কোন ভিটা স্যার শেয়ার ফোর্স? আচ্ছা বড় ভিটা, হ্যাঁ জি স্যার বুঝছি।
আমি কথা শুনতেছি না, তুমি একটু জোরে বলো। আচ্ছা বলো তো, হ্যাঁ বলো।
জি স্যার বুঝতে পারছি স্যার, বড় ভিটা হচ্ছে শেয়ার ফোর্স আর ছোট ভিটা হচ্ছে
ডিফ্লেকশন। হ্যাঁ
বুঝতে পারছি স্যার, থ্যাংক ইউ।
আচ্ছা, আর কোনো কোশ্চেন?
স্যার ওভারহ্যাঙ্গিং বিমে ক্যান্টিলিভার পোরশনটা কোন?
আচ্ছা, মনে হয় কোনো কোশ্চেন নাই। এনিওয়ে, তো তোমাদের পরের ক্লাসে আবার কিছু এক্সাম্পল করাবো, তখন বাকিটা ক্লিয়ার হবে। ঠিক আছে, প্রত্যেকটা জিনিস তখন ক্লিয়ার হবে। ঠিক আছে, তাহলে ভালো থাকবেন ভাই। আচ্ছা,
আসসালামু আলাইকুম স্যার।